Hello, everyone. Thank you for joining us for another live webinar session hosted by EE Tech and All About Circuits. My name is Dale Wilson. I'm the Director of Engineering and Content for EE Tech and All About Circuits, and I'll be your moderator today. Today's session is brought to you by Efficient Power Conversion and is titled Unlocking Efficiency and Precision, Leveraging GaN FETs and ICs in 48-volt motor drives. Let me tell you about our presenter. Federico Uña is a senior application engineer at Efficient Power Conversion's Motor Drive Design Center. Before joining EPC, Federico worked as a test engineer on power test applications for automated test equipment company SPEA. He received a BS and an MS in electronic engineering from Politecnico di Torino. His master's research was focused on power electronics in collaboration with the Power Electronics Laboratory at the University of California at Irvine. Following the presentation, we will have a live Q&A session with Federico. You can submit your questions at any time during the webinar using the Q&A section on the right-hand side of your screen. We will also provide our attendees a downloadable copy of the presentation near the end of today's session. This will be available in the Handouts tab. Thank you so much for joining us. And with that, I'll hand it off to Federico for today's presentation.
Thank you, Dale, for the nice introduction, and welcome everyone to this webinar. Today, I will be talking to you about the use of gallium nitride devices in motor drive applications. What are the benefits that they can bring to motor drive inverters, and what are the main aspects to take into account when using GaN for designing motor drive inverters. So we'll see a little of a landscape of all the motor drive applications using GaN. We will see what are the technical advantages of using GaN in motor drives, a couple of very simple rules to design effectively a GaN inverter, and lastly, a couple of minor information about the reference design boards that we design and that you can buy off the shelf to speed up let's say the knowing of GaN in your applications. So in this first slide, we're seeing a kind of I wouldn't say a graph, but it's kind of a graph that identifies some of the motor drive applications that can be divided into the dimensions of the motor and the current that is delivered to the motor. So when we have a small current and the motor and the inverter needs to be a small dimension, well, that is the land of the power stage. Gallium nitride technology allows to realize completely monolithic integrated circuits that have digital inputs and power outputs without the need of an external gate drivers, and has some additional logic inside. And that low current, small dimension is the land of the monolithic power stages, whilst the small dimensions and the higher current is the land of an inverter made by single discrete GaN FETs. So a typical example of this is an e-bike. While I forgot to mention the typical application example of the power stage is humanoid robots. So motors for joints, both the bigger joints in the ankles, but also the smaller joints in the fingers, for example. And lastly, in the higher current range, where dimensions are not so it's not so important to keep very small dimensions, well, that is when you want to use parallel FETs. It's done also with silicon MOSFETs. It's possible to do it also with GaN FETs. There are advantages, even especially, I would say, at high current and high dimensions, and that this kind of inverters can be found in power tools, in drones, in small electric vehicles, and also in the biggest motors of the humanoid robots. So let's keep this kind of representation of the motor drive applications landscape, and let's bring it to the reference design boards that I have already mentioned. So we have developed a certain amount of reference design boards that can be that are meant for two purposes. The first one is, of course, to make it possible for customers to buy something off the shelf, receive it in a few days, and test it immediately. So this is the first purpose of these boards. And the second one is, of course, to since the Gerber files can be found, to give an example of how a motor drive using gallium nitride devices should be made. So as in the previous graph, we have the boards made with monolithic integrated circuits in the bottom left. In the bottom right, we have one of there are a couple of boards which are named here, EPC 9194 and 9193. This is the picture of just one of them. It's made with a single discrete FET, while in the top there is the currently only board that has parallel FETs for motor drives. So let's go a little deeper into what are the advantages of GaN in brushless DC motor applications, because it's a common myth that there is no benefit in using GaN, since motor drives need to be driven with low switching frequency and with low transitions because of EMI issue. So we'll show that this is not the case. There are positive effects on the overall system due to the increase of the PWM frequency. There are as effects due to the reduction of the dead time, and we will show also a little something of the tests that we have done in our lab. So everything starts, all the future considerations start from the fact that gallium nitride devices switch faster and a little smoother than silicon MOSFETs. Here in this graph, you can see the difference between the transition of an 80 volt rated gallium nitride FET and of an equivalent 80 volt rated silicon MOSFET. So thanks to the faster transition, it's possible to reduce the dead time and increase also the switching frequency because of the lower switching losses. So as I have already mentioned, there are two main parameters on which we can work with. So the increase of the switching frequency has two effects, one on the motor side and one on the inverter side. The one on the motor side is that a smoother current that is feeding the motor has a lower harmonic content. So it's, let's say, a little more pure and makes the motor more efficient in terms of electrical to mechanical power. And the effect on the inverter instead is that thanks to the much lower ripple on the voltage, it's possible to reduce a lot the size of the input filter, so reducing the the cost of the bill of materials and the dimensions of the inverter, which sometimes are important. At the same time, it's possible also to reduce the dead time considerably, and this helps in basically eliminating the sixth the sixth harmonic, and so making again making a little closer to a sinusoidal excitation, the excitation, and so enhancing the torque per ampere ratio. Also, even though in the symbol of GaN FETs you will see the more or less the same symbol of a MOSFET, because there is reverse conduction, but there is not a physical diode. So the reverse recovery is zero. So let's go a little deeper into the PWM frequency increase. On the left, you can see a graph showing the difference in having a 10 kilohertz ripple versus a 100 kilohertz ripple. So all the ripple current, So if we see a sinusoidal excitation that goes to a motor as a sum of the fundamental frequency and the ripple frequency, the ripple frequency is contributing to joule losses, to ohmic losses, but it's not contributing to developing torque. So reducing the ripple current in the phase in the phase excitation is helping in reducing this kind of contribution. While on the right side, it's possible to see the associated power loss in a motor due to the current ripple induced by the PWM effect. So basically increasing the switching frequency from the typical application, so 20 kilohertz, to 100 kilohertz, which is the 20 kilohertz is the typical switching frequency of a MOSFET, a silicon MOSFET inverter, while 100 kilohertz is the frequency at which we recommend to operate the gallium nitride inverters. There is roughly a reduction by a factor of 3 in the switching loss in the motors. So to further analyze this aspect here you can see a similar comparison. On the left there are the waveforms, so the current ripple close to the zero crossing of the phase current and to the top, so to the peak of the phase current, and we have several amps of ripple, while on the right side is the current waveform of the same motor, which is run at 100 kilohertz, which is operated by an inverter run at 100 kilohertz. So in both cases, there is a 46 amp peak current, but in the case of the larger ripple, we have so having the same peak current, the RMS value is a little lower. Or if you want to see it in another way, when you have the same RMS value, when you have a higher ripple, you have higher peaks. And when you have higher peaks in the top left graph, you can see that you are going, if you take the graph of the saturation of an inductor, which is the motor, you go a little deeper into deep saturation or deeper in roll-off. So let's see how it's what we call a DC integrated motor is made. So typically the applications that are made with 100-volt devices, which is the typical breakdown voltage of gallium nitride devices, are battery operated applications. So when a frequency between 20 and 40 kilohertz is used, and because of the fact that there are physically some cables between the battery and the inverter at least 10-20 centimeters long, some EMI filters are necessary in front of the inverter. So inductors, common mode chokes, or big electrolytic capacitor. So it's typical to use an EMI filter, and that is, let's say, that has some limitation due to the switching frequency. So when the PWM frequency is increased, these filters can be, according to the increase in the switching frequency, reduced. So let's have a look about still talking about the input filter, and have a look about the RMS current into the input filter. So when a low switching frequency, and when I talk about low, I talk about 20, 25, 30 kilohertz switching frequency is used, then it's almost compulsory to use electrolytic capacitors. And electrolytic capacitors are not dimensioned on their capacitance, but are dimensioned on the RMS current that they can withstand. So it's hard to optimize these components when uh, when you really cannot use anything else but them. And there are several rule of thumbs, and one of them is to multiply 0.65 by the RMS current of the phase current, and then you get the RMS current through the capacitors, and then you choose a certain amount of electrolytic capacitors that you need to reach that target current that you need. So this makes it even inevitable that in high current applications, the number of electrolytic capacitors must increase a lot. So on the other side, using electrolytic capacitors, using multi-layer ceramic capacitors, they are not dimensioned on the switch, the RMS current that flows through them, but they are dimensioned on the ripple voltage that can be admitted. So at lower switching frequency, it's impractical to use them because it would be necessary to use too many of them. But when increasing from, let's say, 20 to 100 kilohertz, then since the voltage ripple is inversely proportional to the product of the switching frequency and the capacitance, then if you increase the switching frequency by a factor of 5, you can decrease also the capacitance by a factor of 5. And at that point, the number of multi-layer ceramic capacitors that is necessary is small enough to make it possible to have reasonable bill of materials and still a working inverter. And also, in addition to that, there is if you have a look at the graphs of the impedance of the capacitors, there is a sweet spot in the impedance of the multi-layer ceramic capacitors close to more or less 100 kilohertz, which is just one of the reasons why we recommend to operate the motor drive inverters at this frequency. So let's have now a look about the reduction of the dead time. So the dead time reduction is directly linked to how fast the transistor can switch, and the effect of the dead time in the motor drive sinusoidal applications can be seen in this picture. So when the dead time is very large, and this is a typical number for silicon MOSFET inverters, 500 nanoseconds, there are discontinuities in the modulation voltage. And these discontinuities, which can be seen even if in this graph, I don't know if it's high quality enough, I hope it is, they kind of disappear while the time is reduced to a number which is, in this case, it's 21 nanoseconds, which is something that gallium nitride inverter can easily handle. And so if you do a spectrum analysis of these modulations, you will see that clearly that this high dead time is contributing to developing a sixth harmonic in the spectrum, which can be measured, let's say, in even with an oscilloscope, which is what we did, and it completely disappears when it comes to a 21 nanosecond dead time. And again, this harmonic contribution is not developing torque, so it's all energy that is wasted. And energy wasted means, of course, a reduction in the efficiency. So basically, increasing the dead time also contributes to enhance the efficiency of the motor. So now, the last slide about the dead time effect is that let's say we can we can have an overall comparison of the two ways of driving a motor. So the older way using silicon MOSFET devices with 20 kilohertz and 500 nanoseconds on the left, and 100 kilohertz and 21 nanoseconds that time on the right. So the ripple, so the scale of the scale of the waveform is the same. So you can see clearly that the ripple in the phase current is larger in in the case of the 20 kilohertz modulated inverter, and this effect is also evident in the ripple current, which is reported in the red. And the the voltage ripple instead has a ripple which is not so different. So it's a different shape, but the peak-to-peak value is not so different. But what you should look at this moment is the number of components that are necessary and how big they are in the case of the 20 kilohertz modulated inverter and the 100 kilohertz modulated inverter. So in the case of the 100 kilohertz modulated inverter, just two small 22 microfarad capacitors are used, multi-layer ceramic capacitors, while in the case of the 20 kilohertz inverter, not only larger through-hole electrolytic capacitors are necessary, but also um, a filter inductor was necessary to have this kind of smooth um, input voltage waveform. Okay. So let's have a look at some applications, and in particular at the numbers that that come out from some tests that were made. So we are now referring to the same driving differences that I have mentioned before. So we have a MOSFET inverter driven at 20 kilohertz and 500 nanosecond at times, running a certain motor in some conditions, so 400 RPM and 5 amps RMS in phase current. This was made, by the way, with monolithic integrated circuits. And on the other side, we have measured in the same conditions, a gallium nitride inverter operated at 100 kilohertz with 21 nanoseconds at a time. So we have already talked about the differences in the input filter. So in one case we have an inductor and some large electrolytic capacitors. In one case we do not have an inductor and we have just small ceramic capacitors. So the the goal of these measurements was to show that a certain motor, so measuring the output mechanical power delivered from the motor to the load, and measuring at the same time the input power required by the inverter, and showing that the overall efficiency of the system was higher in the case of the gallium nitride. So I'll just focus on the efficiency. So the electrical power, if you measure the electrical power that is flow into the MOSFET inverter and output and out of the MOSFET inverter, so before the motor, and you do the same for the GaN, surprisingly, the silicon MOSFET inverter is a little more efficient. And that is actually not a problem, because the efficiency of the inverters in general, both MOSFET inverters and the gallium nitride inverters, is very high. But what the main difference in the efficiency of the motor. So since the sinusoidal excitation is, let's say, purer in the case of the gallium nitride inverter, then the motor is working in a better way. And so you can see that while the efficiency of the inverter is very similar, the efficiency of the motor in the case of the gallium nitride inverter is much higher. And so the efficiency in the end of the overall system is 6.5 times percentage points higher in the case of the gallium nitride inverter. So another application, something that I forgot to mention, I do it now. This was made on the motor of an electric bike. So later, we have also focused on other applications. One of them is agricultural drones. Agricultural drones are heavy load drones that are used to spray fertilizers and seeds and stuff in the fields, and they need to deliver to fly with kind of high payloads with respect to the drones that people are more used to. So like cameras drones, which are very light. These are much larger drones. They can weigh up to tens of kilograms, which is also tens of pounds, I think. And so the test that we have done in our lab, we bought off the shelf a complete propulsion system. A propulsion system is a system made of the which in a drone can be directly connected to the batteries. So it's made of an inverter on the motor and of the propellers. So we have measured, since in these applications the torque load is given by the shape of the propeller. So the relation between the output power is directly related to the speed of the motor, since also the torque increases with the speed univocally. So we have done tests by running the original MOSFET inverter of these propulsion systems, and then we have characterized it to discover what was the modulation frequency and the other modulation characteristics of the MOSFET inverter, and then we have run it with our gallium nitride inverter with let's say the tips that should be used when using a gallium nitride inverter, and we have measured the input power required to run the motor at increasing speed. And then we have made the difference. So we have observed that it was required more power, more electrical power to deliver the same mechanical power to the propeller in the case of the MOSFET inverter with respect to the gallium nitride inverters. So the and the difference in terms of input power required to run the motor is reported on the graph that you can see on the top right. So on the x-axis, it's reported the motor speed, while on the y-axis, it's reported the extra power which is required by the MOSFET inverter. Just to give you a couple of numbers, in the highest part of the graph, so in above 2000 RPM, the order of magnitude of the power delivered to the motor is 2 to 3 kilowatts. So we are talking about 500 watts power reduction in a range of power which is around 2.5 kilowatts. So it's close to a 20% efficiency increase in the case of the gallium nitride inverter. So this efficiency improvement is given by two factors. The first factor is given to the fact that the gallium nitride inverter used sinusoidal excitation, while the MOSFET inverter used trapezoidal excitation, so 6 block commutation excitation. And this is not only related to the gallium nitride technology, is related to the modulation. But what is the peculiarity of the gallium nitride inverter is that block commutation, trapezoidal control is used in inverters that suffer from very high switching losses, because each one of the legs is not switching during a large amount of the overall electrical cycle, while this is not true in the sinusoidal modulation, because all the switches, all the transistors are always commutating during all the electrical cycle. So here, the key aspect about the gallium nitride technology is that since the switching losses are very low, there's no problem in going sinusoidal even when the current is very high. While that is sometimes a problem in MOSFET applications, and that is why in some applications, some manufacturers still use block commutation. And while this was just one of the two aspects, the other aspect is of course the increase in the switching frequency, because in this case we are comparing 15 kilohertz with 80 kilohertz excitation. We are not done with drones, because we have made the same tests on a different motor, which was instead modulated with a sinusoidal excitation. So in this case, it was a little harder to show the effectiveness of GaN, and so the so in this case, the main difference is that there is a mistake on this slide. I'm sorry about that. So on the left, bottom left, you can see the sinusoidal excitation of the MOSFET inverter, which is operated at 16 kilohertz, while on the right side, you can see the waveform of the gallium nitride inverter, which is not operated at 32 kilohertz, it's 120. I will correct the slides before spreading them. But still, even though they have the same kind of excitation, which is a sinusoidal excitation, doing the same kind of tests, so having measuring the input DC power at the same motor speed, there is still a benefit in using a gallium nitride inverter in terms of efficiency, of course. And also this e- efficiency improvement is increasingly, as you can see in the top right graph, at higher speeds. Of course, there is not only in the case of these applications, maybe sometimes it depends on the drones. Sometimes it's important to have to reduce the dimensions. Sometimes it's not so important, but still, for sure, a gallium nitride inverter operated at a high switching frequency with respect to a MOSFET inverter is physically smaller. So you can save time, you can save volume, which means saving weight in the inverter, and sometimes also cost, because if you have a smaller PCB, then in the big numbers you will also save some cost in the dimensions of the PCB. So there are some rules that is convenient to follow when designing an inverter using gallium nitride FETs. So the a common mistake might be to consider a gallium nitride FET or integrated circuit as kind of a very nice MOSFET. It's important not to do this because they are even though both are field effect transistors, they are made in a different way. So since MOSFETs are vertical conduction devices, they dissipate heat very well from the bottom, while in the case of GaN FETs, which are lateral devices, the um, the thermal resistance toward the PCB is not so bad, even though it's not as good as a MOSFET package. But the thermal resistance on the top side of the device is excellent, which is why they are very good for top side cooling. So in the case of motor drive inverters, as in the case of other applications, it's important to minimize the common source inductance. The common source inductance is the inductance which is present between, let's say, in the path of on the source of the device in the loop of the gate driver, and it's the one which is more responsible for switching losses because it's slowing down the transitions and it's producing only switching losses. So And this is something that is related to the layout, but is then linked to the electrical side. Then in the case of the, let's say, pure thermal side, it's the first layer, the very first layers, especially the first three layers, are the most important in terms of heat transfer to the PCB, which is why it's important to use heavy, let's say, heavy copper layers. So due to the pad limitations, the top layer cannot go much uh, beyond 2 ounce of copper, so 70 microns. But then the internal layers can be made with much heavier copper, so 4 ounce in the first two inner layers is a very good rule of thumb to realize efficient PCBs that are efficient from a heat transfer set point. Then at the same time, and this is valid also for other kind of devices such as silicon MOSFETs, the in-pad vias help a lot in bringing the heat down inside the PCB and spreading it through all the layers of the PCB. So it's very important to place the vias to carry the current and to carry the heat throughout all the layers of the PCB. So thanks to let's say the very good switching performance of the transistors, it's in gallium nitride devices don't really need gallium nitride motor drives don't really need decoupling capacitors, such as other applications like DC to DC converters or silicon MOSFET made gate drivers, as well as soon as a ground return plane is made inside the PCB. So when how to put this? So the electrolytic capacitors take care of reducing of the effect at switching frequency level, while usually the decoupling capacitors are meant for operating at the transition switching level. So we are talking about tens of megahertz instead of tens to 100 of kilohertz. So when interleaving properly the polygons in the layers between the positive and negative DC bus connections, a distributed capacitance is spreading all around the PCB. And so when there is a very a return for the high frequency part of the switching current close to the gallium nitride FETs or integrated circuits, then this distributed capacitance can operate as a decoupling capacitor. And so there is no need to use them. And the transition are still very good with very low ringing, which does not cause EMI issues. So lastly, something that we recommend is today's PCB layout tools have, besides the regular license to design the PCB, have some add-ons made by other companies sometimes that can be used to do finite element simulations to estimate the resistance of the traces and to have information about the current crowding in the PCB. So before releasing a design, it's useful to analyze these kind of aspects, because if you have a high resistance in the PCB that contributes to the heat, and maybe it's also heating the device, so it's something that it doesn't really matter about the efficiency of the inverter, but it matters about the temperature rise in the FETs and in general in the inverter. And also current crowding is also contributing to developing hotspots, which in the long run may lead to failures, which is something that usually people want to avoid. So we have already seen at the beginning a little of a landscape of the reference design boards. They are all found on EPC website. There is a page dedicated to motor drive applications, and you will see the gallium nitride, the EPC device which is related to that board, and you will also see the documentation related to each one of the boards. So we have the EPC 9176 board, which is made with monolithic integrated circuits named EPC 23102. In the future, I'm telling you a secret, there will be also a board which is very similar to this one, which is featuring the EPC 23104 monolithic integrated circuits, which is still a monolithic integrated device, but is a cheaper one because it's a little more resistive. And then we have the reference design boards that are using the discrete FETs. So in the center, you will see EPC 9193 HC. It's available in two versions, both a version with a single FET, EPC 2619, which is a very, very, very small FET. And it's also available in a version with two parallel devices. So it's an example of a parallel device board. We have then, and these devices are QFN, are chip scale package devices made of land grid arrays bumps on the bottom side, which are meant for applications that require the inverters to be very small. While EPC 9194 is made with the QFN device, it's able to deliver up to 35 amps RMS current in steady state condition and go to even higher short-term operations. And lastly, on the right, you can see the bigger one, the biggest one of the reference design boards, which is made by 4 devices in parallel. They are still the EPC 2302 devices, and this board is meant to help designers in designing applications that require higher current, and it can deliver up to 150 amps RMS. And yes, meant for applications such as power tools or mini electric vehicles and stuff like that. So in the future, we have just released a couple of new boards. So for those interested in 150 and 200 volt rated devices, there are new boards coming featuring EPC 2305, both in the single version and in the parallel version, and EPC 2304, which is a 200 volt rated devices meant for 150 volt battery applications. And the same as in the previous case, there will be 2 different boards released in Q3 and Q4 of this year, one with a single device and one with the 4 devices in parallel. And then later in the future, there will be also the boards that feature the EPC 2361 device, which is the same QFN device that you saw before in the boards that I showed you before, but this is less resistive with its big brother, the 2302, because the 2302 had the typical resistance of 1.4 milliohms, while this is a 1.0 milliohm device. So you may have noticed that all the power boards of EPC have the same connector for the controller card. So we have made that on purpose. It's not a mistake. In this case, we have also we have made a broad amount of controller cards that have that are connected to demo boards provided by microcontroller manufacturers. So it's possible to still use the same tools of the controller manufacturers, such as ST, Microchip, Texas Instruments, and Renesas, and plug them directly into any of the reference design boards. So you can choose whatever combination of microcontroller and reference design boards. They will always become compatible, and you can always use the same tools that you used earlier, since the programmers are the same that the manufacturers of the microcontroller provides. So to summarize a little bit what we have been talking about, EPC devices are in general smaller and have better switching performance with respect to traditional silicon MOSFETs, and this affects the efficiency of the overall system composed by the inverter of the motor. And I thank every one of you for your attention. If you are not only interested in motor drive applications, there will be additional webinars on gallium nitride FETs for other applications that you are very welcome to attend, and they will be, of course, indicated on EPC websites. And again, thank you for your attention, and I think that now it's time for Q&A.
Well, great, Federico. Thank you for that presentation. One of the things I really found most interesting was your detailed discussion of using GaN in these BLDC designs and how it impacts that selection of electrolytic versus ceramic capacitors. That was great. We already have a lot of excellent questions from the audience, so I'll remind everyone that there's still time to submit your questions, and we'll try to get to them. Just type them into the Q&A section on your screen. So, Federico, let's get started with the first question here. I think it's a really good one. It is, since the GaN devices do not have a body diode, how do they behave when a motor is rotating by its own inertia and acting as a generator?
Okay, thank you. So they do not have body diodes, but they still have reverse conduction. So the pro of not having a body diode is that you don't have reverse recovery. The con is that the reverse conduction in the GaN has a higher voltage with respect to a diode. So when a motor is rotating with its own inertia, it's still and is acting as a generator, the gallium nitride inverter is still working still have reverse conduction to rectify. So it works the same as a MOSFET inverter, just a little more lossy.
Okay, excellent. The next question is asking, are the current control FETs being used to create an AC signal from DC using PWM?
Yes.
Yes.
Yes, that's how a DC to AC converter works.
Very good. This question is asking, does switching at 100 kilohertz affect the microcontroller's CPU or the ADC requirements? Meaning, since the ADC will have a smaller window to sample the current.
Well, actually, today's microcontrollers do not have limitations in going up to that switching frequency. So the tools to generate the firmware are still a little old, so they may not allow you easily to go to 100 kilohertz, but the microcontroller can totally manage it. And also, yeah, the ADC has a smaller window, but that depends also on sampling on the current sensing method that you're using, because if you're using like shunt measurements, is a little more of a problem. If you're using phase current measurement, it's less a problem. But still, anyways, all the microcontrollers that we're using, and you saw the names of the biggest companies that provide microcontrollers, they all work.
Excellent. All right, this question is asking about in one of your examples, the dead time was 21 nanoseconds, and
Mhm.
he was commenting that they were commenting your transistors have good on-off times. Could you achieve 10 nanoseconds? So that's the first part of the question.
Yes. So yeah, actually, um, the customers that design motor drives, even when they are using GaN, still want transitions to be not too steep. So in the case of DC to DC conversion, you can go down really to 10 nanoseconds, even probably 5 nanoseconds, something like that. In the case of motor drives, you still don't have very fast transitions because transitions that are too fast generate EMI issues. So you still want to slow down a little the transitions, and in that case you cannot go to, let's say, 10 5 nanoseconds at a time. 21 is a good number, 20 30. But still, if you compare if you take a silicon MOSFET inverter for the same applications, that time would be something like 100 200 nanoseconds. So the reduction is still by a factor of 10.
Excellent. And I think the second part of this question, I think you answered is why you don't reduce it. It's just because of that EMI and that kind of thing.
Yes.
Excellent. All right. Now this question I think might be related a little bit to the first question, but it's how do you optimize the reverse current flow without an additional diode in parallel?
So there are two ways. The first one is, of course, to reduce the dead time. I didn't point it out clearly earlier, but because of the higher voltage drop in the reverse conduction, having a small dead time is helping in reducing the losses due to the reverse conduction. If you are doing if you need to rectify, like if you have motor inertia, a waveform, but this is true also for MOSFETs. The best thing is to turn the transistor on and make the current flow through the RDS on instead of the reverse conduction. So if you need to rectify, it's better to do it synchronously by turning on the transistors instead of making it using them as diodes.
Okay, and we're picking up a little bit of static from your talking. Maybe I'm not sure if moving is causing that a little bit
Oh, sorry.
that we weren't getting in the presentation. So I'm not sure what that was. So all right, this question is related to the boards that you showed at kind of the beginning and the end. I would imagine. Do these have any of these have an EtherCAT slave on the boards?
No, I'm sorry, they don't have it.
Okay. This question, what are the capacitors and resistors that you use for snubbers and what is their size?
We don't use numbers because if you do a good layout, you don't really use numbers. So the transition is the switching waveforms are already clean enough not to use numbers.
And I would imagine you probably have design layout information out there on your website for people to see what a good layout looks like, right?
Yes, yes, especially on our book. We are about to release the fourth edition of EPC book,
Mm.
which is all made by my colleagues and myself. So it's full of information about how to do the layout. Yes.
Great. So go check that resource out or reach out to EPC if you want to find that. This question is asking, what sensor are you using for sensing the high frequency currents? Can you provide some names?
Yes, it's all public information on the bill of materials of the boards. So we both use phase current measurement using shunt resistors and instrumentation amplifiers, like the Texas Instruments INA 241, and also some integrated sensors like the ones provided by Allegro and MPS.
Okay, excellent. How do you optimize the motor for a GaN application?
That's kind of a weird question. No, it's not weird. I mean, let's say that it's not always true that the increases in the switching frequency is bringing benefit to the efficiency of the overall systems, because some motors have already reached the optimum switching frequency at 20 kilohertz. So it's more evident in motors that have smaller electrical constants. So motors that have low inductance motors benefit more about the characteristics of gallium nitride inverters.
Mm. Yeah, and that makes a lot of sense. So it's selecting the right mode or the right application for applying GaN where it really is going to benefit. So, all right. Still working through a lot of great questions. The audience, we appreciate your participation today. It's been fantastic. So, this one is asking, do you have any recommendations on the current sensors at 100 kilohertz? I think we kind of already answered that, maybe, but
Yes, so I would say very small ones, there is both Allegro and MPS. Bigger ones, it's Allegro.
okay. Interesting question here. Do you have a book or resource you recommend for motor controller design in general?
Well, we don't have one specific for motor controller design, because we have, the question is actually smart, because we have some books dedicated to DC design. So we don't have yet a motor specific for motor control design, but we talk about motor control design both in the GaN transistors for power electronics applications and GaN transistors in general. So we have two books, and they are both found on EPC website.
Excellent. This one is the gain of the MOSFET sine wave versus the gallium nitride sine wave for a UAV application 30 watts at a 3 kilowatt power level?
I don't remember exactly the numbers. So the gain was, yes, about 30 watts, but the power level was not 3 kilowatts, was much less, because there were two different motors. So that motor at the same speed had much lower input DC power. So in the case of the high frequency versus low frequency sinusoidal application, sinusoidal excitation, the efficiency gain is closer to 5%.
Okay. Here's a flip question. What are the disadvantages of using GaN?
I'm not gonna answer that. No. So it's well, of course, some designers are a little more, let's say, conservative. So it's not something which is bad. It's normal that you're used to use something and you don't want to use the new things. So I would say that the main disadvantage is that it's more challenging to start design with new technology, and because you have to learn new stuff and doing things a little more differently from the previous case.
Okay. What is the cost benefit between silicon and gallium nitride?
So that really depends on the silicon manufacturer and on the RDSON. But often we have competitive prices.
And I think I remember when I was talking to you folks at EPC at the PCM conference last month that one of the things that was mentioned to me is that the GaN solution, the other components are often a lot cheaper, and then the lifetime can be better because they're running at lower temperatures, they're not heating up as much, and so the whole lifetime issue of the cost is really important to think about, and the total bill of materials.
Yes. So yes, it would be important to have a look at these at the system level bill of materials, not only to focus on the price of the FETs, because since it's a new technology, all the design is made a little different, and so other components often change.
Excellent. Let's see. Looks like we got one more here from the audience that'll, well, we actually got more coming in. We're right up the top of the hour. So let's pick one more. How about this one here? So, is any analysis on the EMC impact of different slew rates in motor drive systems? Do you see benefits from reverse recovery ring removal in the EMC performance, or is it primarily slew rate determined?
So we have just started performing some EMC performance comparison between all the solutions, and so I would say that as a first analysis, the main benefits, mainly the benefits, come from how good you do the layout. Not only these benefits are not only related to the device. So the effect of the fact that you don't have a recovery ringing might easily be hidden below a bad layout. So that is I'm not sure if I answered, but it's something that is very tricky to answer and to debug in general.
And then back to your presentation, yeah, it's a slew rate, but then how much ringing are you having, and how many harmonics are you? All those things are driving that as well.
Mm-hmm.
I want to let everyone know that a PDF copy of this great presentation from Efficient Power Conversion is now available for download in that handout section in the upper right-hand corner. There's a couple other resources they've made available, so check those out. Federico, thank you for your presentation and that great discussion during the Q&A.
Thank you for the time and for the show.
Yeah, and thanks to the audience again for your great questions. Sorry we couldn't get to all of them. You can reach out to EPC and get other answers. In just a moment, you'll be redirected to Efficient Power Conversion's page on All About Circuits. You'll be able to view this session on demand by using the same link you used to view the webinar. Thank you all for your time, and we look forward to seeing you at another live session again sometime soon.